Hi everyone, this is the proof of Euler's method in general cases. So let me review the special cases and the result quickly to explain what I mean by these general cases. So context was the following. We have first order differential equation in standard form and very highly nonlinear cases you usually look at. And we assume it has a solution, which is actually the fact that if this function as a two-variable is continuous partial, especially at y, and it's continuous, then it always has this a solution, and it's actually a unique solution. And all these hypotheses in the special cases are complicated, but I think it's necessary. First of all, this is where we start, y equals y0, and this is the differential equation. And we put this upper bound and lower bound in regard to the solution here. We don't know what the solution is, but we know it exists, and continuous and differentiable and all that. Therefore, it has a maximum minimum. So put large enough r up top, to the top and to the bottom, such that this top and bottom includes all the graph in here. And this beta is wherever you want it to go up to. Usually it's a free choices. And here's there's no problem putting with this r and no restrictions in here so far. Now restriction kicks in to this beta part. So it goes like this. First, m1 is going to be the maximum value of this continuous function on this box here in 0 and in beta d. And condition we're imposing on here is that this beta must satisfy this inequality. R is the thing that we choose, and m1 is the maximum value on this plate. So if I change that r, m1 changes. So it's kind of the subtle condition, but later on you will see this is not that restrictive condition. But under this condition, we proved in an earlier file, an earlier video, that Euler method works. Now this is the beginning of the general case. Suppose we're looking at that rectangular box that satisfies the condition just like we said before. And what is going to be different in this general setting is that we're going to apply that little tiny box in several times. When you do the second box and the third box and so on, you will see the beginning gap is no longer the same. If you look at the special case, we started here and ended here, and that was it. And of course at the beginning we set our initial value z0 to the same as y0. But when you repeat this over and over, you take the gap you created by doing this process as we did in the special case, and then do this again, but we have to carry that initial gap. So in this setting, the difference is that we have this slightly different initial gap value, and then it possibly widen the value later on. So this is the situation. There are a few more subtle things to watch out, exactly what the size of this height of this rectangle is, but I'm going to explain. But basically, I'd like to claim that we can guarantee that if you start from here, g0, this initial gap, not necessarily 0, and if you repeat it n times, if we have the property that all these Euler points value are staying inside this rectangular box, if we have that property, which is usually what this beta restriction on the beta is about, if we can guarantee that xk and zk, they stay in this box, we have this calculation again. This m2 and m3 were absolute constant, and m2 were absolute value of the second derivative value, this one divided by 2. m3 was maximum value of absolute value of the partial of f of xy, the right hand side of the differential equation. The key thing is that these are absolute constant depending on this box in here. And we're about to change the box, so we have to be careful what we mean by exactly m2 and m3. But if we have a little box, and if we guarantee that this point is staying inside in here, we have this type of a result where this alpha is 1 plus h times m3. So I'm going to show you the general setup a little bit more carefully, so you believe we still have this type of thing with an absolute constant m2, m3, and m1 involved. Alright, here's the general setup. Suppose we have this rectangle. We want to go A to B, and this, we're going to start here A, and we want to calculate this V value is not going to change. Only thing we'll assume is we have this nice continuous and differentiable, infinitely differentiable solution here, and we want to go A to B, and there will be no condition put on A relative to A or the function. You just want to calculate this B. Now this is our box D, and I'm going to explain that's our choice of A and B, how wide this rectangle is. So let me explain the choice of our top value and the bottom value. We start from y0, and before we have r2 above and below, but we're going to have slightly different values along the way as you repeat this, because we can't apply it directly to this entire rectangle. We divide it into pieces. That's why we have to adjust this upper bound and lower bound a little bit. As you can see, this A here is a maximum of this function value from A to B. This is our choice, A and B, and minimum value in B. So you go from the top, the maximum value, R more, and from the bottom, the minimum value, to R down. So this is how wide our thing is, and R is our choice. R can be big, and in general what happens is if R is big, then probably you have to take this first rectangle that we're going to apply our special case result a bit smaller. If it is tight, we may have a better result for the first rectangle to use with our special case proof. So that's our setup, that's our D. And we have to consider this maximum minimum value, and here they are. Well, before we do that, I think it's better to just say this one first. This B minus A, there will be absolutely no condition on n B, how small this B should be, and so on. So we can assume that the situation where B minus A is too big to be considered as a special case. So especially for that case, we want to show this our Euler method works. So here's the setup. So these are the some constants involved in our inequality. The first, the maximum of function value of that two-variable function in the differential equation. So that's our D, the maximum on that D. M2 was this maximum of this, pretty much the half of the value of the second derivative of our solution, for which we only know the existence, not anything explicit. So that was considered x between A and B. And M3 was the maximum value of this two-variable partial derivative, again on that big plate D. So these are M1 and M2. The key thing is that if you consider smaller rectangles that it is shown on here, for example, this M1 and M2, M3 still serve as an upper bound on here and there and there. Maybe it's not exact maximum, but it still serves as an upper bound of these values if we're looking at smaller rectangles here. Because that's the highest over all rectangles, biggest rectangle, so any subregion must serve as a for this any subregion, these values must serve as a bound, upper bound, nice upper bound. So that's the good thing, that we use this one still for the smaller one, and it works. So here's our choice of a beta. This time there's a 2. Then in the special case there wasn't a 2. The reason there is a 2 in here is because this initial gap is a little bit more, so that we have to make it a little bit smaller than usual, R over M1, such that this type of initial gap, a positive initial gap, is not causing too much a problem. So the beta this time is smaller than half of the R over M1. This is the upper bound we put on here in the special case. So B is probably a lot bigger than this one, so we can only apply our special case to this value here, which is the beta. And then I can choose this beta, and as long as it's smaller than this one. So you can probably choose some real number such that A over B is exactly integer multiple of a beta, so that when a repeat is exactly integer multiple, so when you repeat this special case a couple times, you're not left with some odd size of a chunk. Just exactly the beta and beta, 3 times or 4 times beta. You can always choose that beta in here. So that's what we mean by this beta here. That's exactly this size, and that size, and that size. So for simplicity, we assume beta times 3 is exactly this b minus a. But the idea pretty much shows how the general proof goes.